Alright, what is going on, guys? Things are going to get interesting, things are going to get fun here. I'm not going to do in every video animations, but we're going to get into the covariant derivative for QCD. After this, we're going to build a matrix theory for quarks, and then after that, we're going to start getting into some more advanced stuff, trying to learn QCD from a different perspective here, but still understanding all the basics and even some of the advanced stuff as well. And that's going to be things like gauge fixing terms and ghost terms and gauge theories and gauge field theories and lattice QCD, perturbative QCD, and so much more. So let's go ahead and get started. Make sure to hit that like and subscribe button, and let's go. Alright, so the covariant derivative in QCD. This is a very, very interesting thing, and we're going to draw an economic analogy to this as well. Let's get some of the math out of the way. We're going to do the economic analogy, and then we're going to come back to the physics. So, now we've dealt with group theory and gauge fields. Let's dive into our equations of motion. When we do this, we are going to start realizing that we are going to run into a few problems here. One being the gauge fixing problem. The idea here is that there's going to be, we have this Lagrangian. The Lagrangian is well defined and everything, but its propagator isn't. And because the propagator isn't defined, again, I'm sort of going on a tangent here. This is going to be the topic for the next, not the next video, but the video after that. We need to add a term. That term is going to be the gauge fixing term. But when we have the gauge fixing term, now that the propagator is going to be defined, we now lose gauge symmetry. So to regain that symmetry, we are going to add something called ghost terms. And the ghost terms, that's going to preserve something called BRST symmetry. So we'll get into all of that. But again, the idea here, I diverge a little bit, but the idea here is that we now have this Lagrangian this is our Maxwell Lagrangian. And this is our Maxwell equation of motion, right? So this is our Maxwell Lagrangian, Maxwell Lagrangian. I think Lagrangian is an A there. And this is our Maxwell equations of motion, E of M. So the idea here is now we want to do the same thing for our non-abelian case, right? So because the Maxwell case was the abelian case. So, and in the non-abelian case, this is going to be the Yang-Mills equations of motion. And this is going to lead us into the concept of the covariant derivative, how this thing here is going to differ from the non-abelian case. So we start with the Lagrangian here. And our Lagrangian looks like this. It's going to be proportional to the trace of this thing. And the reason we put the trace here is because when we flesh out everything with our T matrices, or Gell-Mann matrices, their trace is going to go to 1/2, and so that's going to make this 1/4 go to 1/8, and so then we have this. So the trace is now effectively out of the question here, and we just have this thing. So how's this going to work? Well, we have our Euler-Lagrange equations, right? So we can use the Euler-Lagrange equations on this thing to develop our equations of motion, right? So that's the name of the game here, right? So let's do this one is going to be on this side. This guy here is going to be on this side. Just the parentheses, right? So, and then we'll add this derivative later. But we could see here, here's our Lagrangian. This thing is being squared, so this is just this is just a product rule or the power rule, however you want to call it, in calculus. But we get this thing. This is going to be the product rule, right? Yeah, I don't remember the names of stuff in basic and elementary calculus. But then this thing here is that's this thing. This is our field strength non-abelian tensor. And so the derivative is going to be just this right here, because they're these guys go to 0. These are just constants with respect to the derivative with respect to this thing, right? Because this is not d a mu, right? So these terms aren't there. So these things are constants. They'll go away. Those are 0. And because those are 0, we're just left with this term right here, which is right here. All right, so far so good. Again, you can pause the video if you want me to slow down, or if you want this to slow down as well. But this is intended to be a comprehensive course on QCD. So, okay, so we have this guy here. So that's right here. The constants we'll take out, and the derivative now of these guys is going to be so the derivative of this, we need to take the derivative of this and then add the derivative of this, right? Because this is the product rule. And to do that, we need to use covariant derivatives because we have we need to make sure these go to 1, right? We need to use the Kronecker deltas, right? So we have A at top here, A, which we could just highlight some of these, right? A, and then D and D, and then sigma and sigma, and then just to highlight a few of these here, C and C, and let's do another color, mu and mu, right? And then do black for nu, or black for mu, right? So you can see how this works, right? So we have these two guys right here, and then these two guys right here, and then we need the A and nu here to sum over for the Kronecker deltas. That's a bit messy. But the point here is that these two guys are the same thing, right? These two guys are the same thing. And effectively what we're doing, right? Effectively what we're doing here is we're just saying, I'll erase that really quick. Here's C and mu, and here's D and sigma, right? So C and mu, D and sigma. That's really what we're doing. All right. This collapses, so since these are the same thing, this is going to collapse down to this. We have mu, or nu and mu, right? Nu and mu. So that's going to be nu and mu, right? That's those guys. And then we have this right here. And because these are the same thing, it's going to be 2 times 1/4 is going to give us the 1/2. And then we get this guy right here, right? We're just putting G over here, our structure constants, and then G and A are right here. And then what we get is going to be this right here, right? Because this is going to be anti-symmetric. We haven't really talked about the structure constants, but for right now, to get from here to here, we have anti-symmetry in our structure constants. So anti-symmetry in F, those are going to be our structure constants. We'll talk about those more in the next video as well. And that's where we develop, and the next video is going to be where we develop our matrix theory for quarks. And so now, so we get this. We just put all the constants and the G and the A in brackets. And so we have this thing right here. All right. So far, so good. Let's now take a look at the other part of our Lagrangian. That's going to be this part right here. We do the same thing, right? So here's the same thing. These things are squared. Sorry, so we bring the 2 over. This gives us the 4. This thing here now, this guy right here is going to be applied to this guy, and then it's going to get multiplied to this guy as well. And what we see here is that because these are derivative terms, here's a derivative term, these just go to, these essentially just go to 1, right? So we have this thing twice, right? Because the whole thing is being applied over twice. And so we get this guy right here. This guy right here then is going to be, this is anti-symmetric, right? This is anti-symmetric because we have rho sigma, sigma rho, mu nu, nu mu. Okay, that's how we were able to do this. And so now we have this guy. It's because this is anti-symmetric, this becomes positive, so we have this bit minus this bit, and so negative 1/4 minus 1/4, that's going to give us negative 1/2. All right. And then we take this mu derivative here, and that's going to be right here. So putting these two things together now, we get this guy right here, and then this guy right here. And then, right, because this guy right here, we just take we're moving the derivative over. Then we move this guy over here, and this guy over here. We multiply both sides by 2, and we have this guy right here. We're defining now this thing to be our covariant derivative. So the covariant derivative is d mu plus g f a b c a b mu, right? There's a little bit of nomenclature stuff going on here that doesn't really matter that much, but the idea here is that this is a function of space-time, which is why we have the mu here. It's a function of space-time, but the reason we have mu again is because it's got the mu components. So this is a 4-component thing, and the B refers to which this thing applies to one of the Gelmont matrices. So, okay, so we have this thing, right? This thing is our covariant derivative, this big D. And so this is our covariant derivative. We define it a little bit differently. We absolve all the constants, the structure constants, into G, and we allow this to be complex. And when we do that, our most general covariant derivative for our gauge field theory is this guy right here. We can contrast this with the general theory of relativity, what the covariant derivative looks like there. We have this thing, the Christoffel symbols. These things compensate for the change in the basis vectors as we move from point to point on a manifold. And so we can almost sort of think of these things as compensatory objects that get appended to our normal derivative, and they have some meaning to them. And what we want to do now is actually look at what this meaning actually does, or what this term actually does. And a good model for this is going to be an economic model. I know I always go back to economics for this, but it's actually super interesting. And yeah, let's get into the economic model here, because this is going to be it was eye-opening for me when I started getting into the analogies between gauge field theories and economic systems, and I kind of want to share this with you guys. So let's do this. So we can see how these independent functions serve to compensate for something just as the Christoffel symbols do for general relativity. However, the Christoffel symbols, they all have space-time indices, right? Mu, nu, and lambda are space-time indices for general relativity. However, here we have mu, which is a space-time index, and a, which is not, right? So this thing here, it might be a compensatory object, but we don't know how yet, because it's not directly analogous to the Christoffel symbols in this way. It's only directly analogous in the sense that the covariant derivatives look very similar to each other. So let's go back to financial systems to understand this. So suppose we have a factory A, and this is creating widgets of some sort. Okay, there are different ways to measure the durability of these widgets, right? So we're going to call the durability of this widget A mu, okay? And this is a function of time and space, okay? And so the durability of these widgets can be measured by resistance to heat, pressure, corrosion, tensile strength, and so much more, right? So there's all these things we can use to measure the durability of these widgets. The factory has its own local quality control protocol, and the order by which we apply the control protocols matters, right? So suppose we have protocol 1. Protocol 1 says we're in factory A using protocol 1. Protocol 1 says that, okay, we're going to do a heat test first on this thing. Okay, so protocol 1 we do a heat test. So this is step 1, and then step 2. I really don't like how this does this. So here's step 1, and then here's step 2. Step 2 is to measure its pressure strength or whatever, tensile strength, whatever you want to call it. And we could see that in the end, we have a deformed object, right? So you heat it up. That you can use some intuition here. If you heat it up, you weaken the bonds in the widget. When you weaken, all the kinetic energy added to the widget makes it malleable, right? And so when we add pressure, then the malleability gives, okay? But then if we do protocol 1 in reverse, the pressure might not make it malleable. So nothing happens, right? So we do a pressure test, nothing happens, it seems to be strong. And then we do a flame test, and the shape doesn't really do anything. It doesn't melt, right? Pressure, when you apply pressure to something, that doesn't necessarily mean that the thing is going to melt. So the point here is that protocol 1 in reverse did not result in the same structural integrity of the widget, right? So, okay, that's all fine and good. Let's now take a look at this. And so what I did here is I said, okay, step 1 was to do fire strength, step 2 was to do pressure strength, and the outcome was something that looked like this. Protocol 1 in reverse, the outcome was something that looked like this. So now suppose the widget was sold to another factory. This is going to be factory B. And this factory uses the widgets as well. Factory B also does a durability testing on the widgets, but their metrics for doing durability testing are not the same as for factory A. So therefore there must be something which contains the complex rules for converting factory A's measurements to the language for factory B. Okay? So here's the idea. The raw change in the durability, which was a mu, okay? The raw change in the durability, that's going to be given to us by this d mu, right? That's just the change in the durability from factory A to factory B, okay? But then there's going to be a protocol adjustment, right? So we had the protocol here that told us how to do a durability test for our widget. We need to translate that protocol as we give that to factory B as well, right? So not only are we transferring the widget itself with its durability, and a mu can be thought of again as the durability of the widget. Here we are actually, this is the complex set of equations that tell us how the protocol has to change as well, right? Because two factories aren't the same thing. They have their own protocols and so forth. So that's how I like to think about this, right? So in our economic model, we have commodities being moved around, but it's not just the commodities that are being moved around. It's the commodities plus how you use them, okay? And so, okay, so we have this A mu, we have our durability test as well, okay? Durability test has to get translated, and the durability itself there's also going to be a change there because the metrics by which this factory uses to measure the durability of some object is going to change, right? So that change is encapsulated here. The change in the protocol adjustment is going to be encapsulated in this thing. All right, so that's the economic analogy. Let's go back to some physics now. The widget represents a hadron in physics, which is a composite particle made of quarks and gluons. Okay. The most common hadrons are protons and neutrons. Right? Those are the things, the center of atoms. Right? You have protons, you have neutrons. Those things are at the center of atoms. The number of protons identifies the identity of the atom itself, and the number of neutrons identifies the isotope. Right? That's chemistry. The durability of the widget represents the quarks. okay, inside the hadron. Quarks have the property called color charge, which is analogous to electric charge. And since there are different ways to measure the durability of the widget, we need a protocol adjustment manual. Okay? The protocol adjustment manual is going to be represented by the gluons. The gluons are the force-carrying particles of the strong nuclear force. They are the agents that carry the color charge from one quark to another, binding them together. This is a crucial distinction. In the strong force, the force-carrying particles, which are gluons, also carry color charge, which is why they interact with each other and make the theory non-abelian. So, and we'll get into this, right? Because when we start looking at the matrices, which is what we're going to look at in the next video, a matrix theory for quarks, when we look at this equation again, A mu equals A mu A t, A, we're summing over A. This thing, in the Gelman case, we have 8 of them, right? But they're 3-dimensional. So there's 8 3-dimensional matrices. What that's going to do is, again, it's going to give us this 3 by 3 matrix, but there's 8 independent things in this matrix, right? Those are the functions. We've talked about this. I don't know if I actually have that that matrix here. We'll get to that yet, but we've seen that. It was a 3 by 3 matrix, but there was 8 independent functions within the entries of those matrices. And so that was, and we'll get into that more in the next video, but that's how we distinguish quarks from gluons, right? And so what we have now are gluons. We have gluon fields. We have our quarks. Quarks are like the widgets again. The gluons are the protocol adjustment manuals, and the hadron itself is the combination of the quarks and the gluons. All right, so now we have a solid economic framework for how we can understand non-abelian gauge fields. We have this thing here. This is our field strength tensor. This is the value difference when commodities affect the value of other commodities. We talked about that in the last video. And then we have, or in the last few videos, and then now we have our covariant derivative. This is how value changes when the concept of value is different somewhere else. Okay? We need the concept of value is different somewhere else. That means that this thing accounts for how the raw value changes, and then this thing again accounts for the change in how you measure that value. Okay? That's going to be, again, the protocol adjustment manual. All right. This implies that there is an internal sum over labeled indices within the covariant derivative to account for each of the gluon fields. The covariant derivative can therefore be written in matrix form. So this is in matrix form, right? Because our original covariant derivative was d mu, right, minus I g f a b d a d. And so now we just, here we add a 1, right? So that's going to be our Kronecker delta. And then here AD, that sums over the T matrices, right? So AD. And then we can, these are just dummy indices, we can relabel them. But the idea here now is that we have this thing right here, right? We have this in matrix form, we have these guys, right? Our covariant derivative matrix has entries then that look like this, right? So 1, 1, 1, 2, 1, 3, 2, 1, 3, 1, and so forth. And this is what all of them look like, right? So here's the thing, right? So these things are 1, 1, 2, 2, 3, 3. These are going to be the diagonals, right? These are going to be the diagonals, and then the off diagonals are going to be where the Kronecker delta is where I doesn't equal j. And so we can get rid of that because that's going to be 0, and we're just left with this part here. So in the end, putting this all together, we have a covariant derivative that looks like all of this. All right, and you could take the determinant of this, you could take the trace of this. That is not really, it's not really of interest to us right now, but because we're coming up on 30 minutes here, the idea here is that we can think of this as a matrix now. We're developing now a matrix theory for our non-abelian gauge fields, or our non-abelian, for our non-abelian gauge fields. So what we have now is we have a matrix for this equation, right? We have a matrix for this equation. This was A mu TA. Now we have a matrix for d mu. That's this thing right here. That's going to be d mu. How do I want to do this? Let's just do it like this. We have d mu plus I g a a, right? We just do it like that. And so this is what we have, right? This is our thing that is our matrix field, or matrix valued. We're calling this our matrix valued gauge field. And this is a matrix valued gauge derivative. Matrix valued gauge derivative. So what I want to do just in the last few minutes here is talk about how we can what's next to come. Next to come is going to be a matrix theory of quarks, right? So matrix theory for quarks. Okay. The quarks, again, were these objects here. They have this thing called color charge. And the idea here, again, is that we have this 3x3 matrix, okay, given to us by our Gelman matrices. Because it's 3x3, we have these 3 independent internal variables, which is the color charge. After that, we're now going to be on a firm ground to be able to start diving into some more advanced stuff. And so the first thing is going to be gauge fixing. Gauge fixing. That is, so in an economic model, this is actually kind of interesting. You can have a commodity that is worth, say, $20, okay? But you can convert that to 400 yen or whatever, or in euros or whatever. And the gauge fixing, what that's going to do is going to help us not overcount the we'll see how this works, but it's going to help us not overcount for the amount of descriptions that we have available for the value of something. Okay. And so we're going to have gauge fixing. That's good. We're going to take a look at our Lagrangian. We're going to see that it's gauge invariant, but it doesn't have a clear propagator. Because it doesn't have a clear propagator, we need to add this gauge fixing term. But when we add the gauge fixing term, we are going to lose our gauge invariance. So to gain back the gauge invariance, we introduce this thing called ghost terms, right? And so there's going to be ghost terms. There's going to be a lot of nomenclature. There's going to be a lot of nuanced things here when we start talking about this, because there's going to be some names to remember. The Feynman T. Hooft. I don't really know how to pronounce his last name, but there's going to be that gauge. There's going to be the chi gauges, the chi gauge families that we're going to look at. There is going to be the BRST symmetries. That is going to be closely related to our ghost terms and what that all means. Ghost terms, these are, hopefully by Halloween we'll be talking about these ghost terms. And that is going to be super, that's going to line up well, probably, hopefully. And so, yeah, so that's where we're going from here. Then we're going to start getting into some more advanced gauge field stuff. Because fundamentally this is gauge fields, right? This all comes down to gauge fields, right? Gauge fields, again, being these things that make Lagrangians invariant. We want the physics, again, of all of this to be invariant under local and global symmetries. That's why we're doing all of this. All right. So with that being said, make sure to hit that like and subscribe button, and I'll see you guys in the next video.